We are now in Module 7 of Hydrogeology. In Module 7, we'll talk about the modeling of groundwater flow. I've divided this into 4 videos. The first one will be, why do we model groundwater at all? In the second video, I'll talk about some details about groundwater modeling. In the third video, I'll demo some software to show you some techniques and approaches to groundwater modeling. And finally, in the fourth video, we'll look at a case study of a report of a groundwater modeling activity. We have some learning goals for this module, and here they are for the entire module. Let's highlight the ones that will be the focus of this current video. In particular, we will look at why groundwater models are constructed, what kind of questions need answering by constructing a model. And I want you to understand some of the nature of model flaws. Every groundwater model is flawed, and you need to understand why and how and what you can do about it. So there's issues of non-uniqueness, the parameterization, conceptual flaws, and finally I'll cover what is needed in order to construct a groundwater model. So let's begin. Vocabulary. We'll be talking about finite difference and finite element numerical methods. These numerical methods are built on grids and nodes of points, which have boundary conditions and initial conditions. And the models can either be steady state or time dependent, the diffusion equation. I've included some of the terminology that comes from the field of partial differential equations. You have Dirichlet boundary conditions, which are head specified at the boundary, or Neumann boundary conditions, in which flux is specified at the boundary. A steady state solution is an elliptical form of the differential equation, while a diffusion equation, which has the time dependence, is a parabolic form. Groundwater models in professional applications use terminology of validation, calibration, verification, sensitivity analysis, and prediction, and we'll cover exactly what those terms mean. And finally, but very importantly, we'll talk about how groundwater models are non-unique. So why create a groundwater model? Clearly, a model provides quantitative answers to questions you might have about the nature of groundwater. But a model executed well is an extremely intensive project. It requires a lot of effort. And a first question to always ask is the effort justified? So what kind of questions are in need of answering? Well, here's a few. How much groundwater can be removed without negative consequences? And negative consequences can include decreases in stream flow, which might negatively impact salmon recovery efforts in a Puget Sound or western United States stream, or it could impact downstream access to irrigation. Groundwater pumping near oceans can result in encroachment of salt water. And so the question is, how much water can be pumped without encroachment of salt water to water production wells? Then there's questions of how much the water table will drop if a certain level of pumping is undertaken, and what kind of surface substance might be resulting from the drop in the water table. And there are many other questions involved in negative consequences associated with groundwater utilization. Also, there are questions of evolution of contamination. Where are contaminants going? How long does it take contaminants to get from a source to a location where it has impact? And once it arrives, what are the concentrations of contaminants? And finally, can we remediate and remove the negative consequences of contamination? So let's consider what is required to make a model. Clearly we have to start with all the inputs and all the outputs of the groundwater system, which means we need to know something about precipitation and evapotranspiration. We also need to know the physical configurations of our system, the location, extent, thicknesses of aquifers, and the same for the confining layers. We need to know the nature of the boundaries, variations of transmissivity and storativity within the aquifers. We need to know the connection of the aquifers to surface water. We need to know the potentiometric surfaces, i.e., what are the hydraulic heads at locations around the model space. And we need to know something about recharge and discharge of the aquifer system. And there can be the natural recharge and discharge, and there can be artificial recharge and discharge. For the artificial, we need to know the locations of the sources and the amounts. Now, for contaminant flow, we need additional information, and explanation of some of these terms has to wait until modules 8 and 9. There's solute transport, that's the stuff dissolved in the water, and dispersivity, densities, concentrations are all properties of the solute that need to be understood. We need to know the contamination sources, their location, the strength of the contamination, and something known as the retardation factor. So let's jump right in. All models are intrinsically flawed. No amount of time, effort, or money can fix this. So what is wrong? All models are intrinsically non-unique. Non-unique means there's more than one arrangement of the subsurface that will give rise to exactly the same set of observations. Models are all built with incorrect assumptions. Now, you don't want to make incorrect assumptions, but often you inevitably do because you do not know enough about the system. All models are also suspect, since numerical techniques may not converge or may contain other numerical errors. So, despite these fundamental weaknesses, much time and energy has been and will continue to be invested in models. The question is, of course, why invest so much time and energy in something that is intrinsically flawed? Well, models do have utility. Models can provide insight. Models provide quantitative guidance. You want a quantitative number, how long, how much, how far, a model can give it to you. And all the models produce professional graphics that make the credibility of the model seem quite high. So, but models can be simply a facade, a nice set of graphics that are not connected to a physically reliable description of the subsurface. Models can be based on little or no factual information or information that is entirely incorrect. So let's talk about some of the problems of models and the uniqueness of models. A model requires parameters. Parameters require observations to constrain them. You need at least one observation to constrain one model parameter. If we are modeling Earth's interior, there are an infinite number of parameters needed, at least one parameter for every point in the space. Of course, you can't know the value at every point in space. One can only make a finite number of observations. And there are two very common problems associated with this intrinsic problem of Earth being represented by an infinite number of parameters and only a finite number of observations being made. Number one is you can have undersampling. Undersampling is simply enough. You don't have enough observations to realistically constrain what's going on in the subsurface. And finally, you could have an entirely incorrect conceptualization of what the subsurface looks like. Let's talk about undersampling. And I've drawn a cross-section. This is actually based on a real-life problem that occurred in a Scandinavian country in the process of prospecting for metallic ores. 2 drill holes were placed in the ground, and the first drill hole intersected a ore body, as shown in blue. A second drill hole was drilled some distance away, which intersected the ore body at a slightly deeper depth. And taking a look at the well logs from these 2 wells, it was an entirely appropriate idea to imagine, to conceptualize the ore body as being a linear feature extending from the location of the one drill hole to the location of the other drill hole. Imagine the surprise of the company when they dug a hole in the ground represented by this pit, and instead of intersecting the ore body at a reasonable depth, they found nothing at all, no ore whatsoever, even at the deepest depths of the excavation. And why was that? Well, the actual shape of the ore body, it was folded strata, it was not linear strata. The ore body was distorted into tight folds, and in fact the 2 drill holes managed to capture the apex, the top of these synclinal structures. And so when they drilled or when they excavated the pit in between, they failed to intersect the ore body at all. So this was definitely a problem of undersampling, and as a result of the undersampling, they had an incorrect conceptualization of what the ore body shape was. Let's talk about other incorrect conceptualizations. Well, let me give you a humorous example, which was actually published in the science journal called Science. It was all based on this well-known truth that the moon is made of green cheese. At the time of the Apollo exploration of the moon, seismic velocities of several cheeses were measured in the laboratory and compared with the seismic velocities measured through the lunar regolith using instruments from the Apollo mission. And here's the table published in Science. Authors were Schreiber and Anderson. They had the materials, Swiss cheese, a Norwegian cheese, an Italian provolone, an Italian Romano, cheddar, Emmentaler, and Munster cheese. And you notice the velocities range from about 2.1 kilometers per second down to 1.6 kilometers per second. Well, the measurements on the lunar samples fell exactly in this range. Velocity of 1.8 for lunar rock 117, and lunar rock 10046 had an even lower velocities. Well, looking at this table, it would be easy to imagine the moon made of a mixture of green and blue cheese in order to make the moon entirely out of green cheese. Now that's humorous, but many incorrect, equally silly, incorrect conceptualizations may plague any modeling effort. And so what kind of conceptualization errors are very typical? Well, assuming layer cake geology when structures may be much more complex. Assuming that the subsurface is both homogeneous and isotropic may be an incorrect conceptualization. It's an incorrect conceptualization to assume that all faults and fracture systems within the study area have been successfully located. Often, boundary conditions may be forced in a model that are different from the natural systems. Finally, assuming that observations are free of error is an incorrect conceptualization. So we could go on with other conceptualization errors, and it's up to you in any modeling effort to be wary of where you may be making such mistakes. Now let's talk about models being non-unique. What does non-unique mean? It means that more than one model can provide exactly the same observations. So let's see why this is the case. First of all, we can define a forward problem in groundwater flow, and the forward problem can be written down as this simple equation, Darcy's law, which says that the flux of groundwater is going to be equal to the product of the conductivity times the gradient in hydraulic head. So a known hydraulic head gradient in location R, a known hydraulic conductivity at that same location, allows you to exactly calculate what the flow of water is at the point R. Now, we are often trying to do the inverse problem. And what's the inverse problem? It's predicting the hydraulic head at point R based on integrating Darcy's law. And so here we have an integral relationship where the hydraulic head is equal to the head at the point R naught minus an integral of the quotient of Q divided by K integrated over the path from R naught to R. Now this integral representation highlights non-unique ideas, because more than one set of conductivities and flow paths can give exactly the same hydraulic head at point R. All that matters in the integral is that the integral be the same, and you can get the same integral for a variety of values of Q and K. Changing Q and simultaneously changing K will change that quotient, and changing the path over which the integral occurs can accomplish a same value of H for different values of Q and K. So, bottom line is, multiple models will exactly fit the same observations. And there's no cure for these model parameters, model problems, but if you have good geologic insight and knowledge, that can help mitigate the conceptual errors and mitigate problems associated with non-uniqueness. You can eliminate certain models as not being geologically appropriate. Having more data is helpful, but you need to have judicious selection. Randomly accumulated data may not be as useful, and getting more data will not fully remove non-uniqueness issues. You need an appropriate spatial and temporal distribution of data. And so this brings in the idea that modeling is a continuous process. You examine the predictions from a draft model, you extend or revise your data collection associated with the model in order to obtain data in areas where the data can have the most impact on making a decision of how to design the model. You then revise and refine the model, taking into account the new information. So, models always are terminated when budgets and timelines have been expended, but a model is never complete. There's always more work that can be done in order to improve the ability of the model to realistically predict the behavior of the subsurface. Let's talk about professional expectations with groundwater modeling. And these are encapsulated in a few terms. Validation is the process by which a computer code has been checked using standard problems and gives the expected answer. In other words, you would be expected to use a validated computer program in order to solve a particular groundwater modeling problem. Groundwater models are calibrated by examining values of hydraulic conductivity, by examining heads at your observation points and adjusting hydraulic conductivity parameters within the model in order to better match the observed heads for a steady state situation. Verification involves a transient event, checking that if you do a drawdown of a well or pump down, that the model again correctly predicts the time dependence of hydraulic heads. Sensitivity is a process by which model parameters are adjusted within some reasonable bounds, and you examine how predictions change as long as parameters fall within the expected range of behavior. Finally, you make predictions using your groundwater model, and that would be the result from the groundwater modeling effort. So that brings to the end our discussion of why model groundwater. Coming up next, I'll consider some of the details associated with the creation of a groundwater model.